Recording. And welcome back, everybody. This is the Virtual Residency Workshop 2023. It's Wednesday, June 28th. And our final session of today is Debugging, Profiling, and Tuning, presented by Prasad Maddumage of Corning. So Prasad, I pass it over to you.
Thank you, Henry. Let me share my screen first. Hey, can you all see my screen?
Yes.
Okay. Welcome, everyone. Let's talk about debugging, profiling, and tuning. I'm Prasad Maddumage, and I'm an HPC consultant at Corning Inc. Okay. Just few fair warnings. So, although I'm talking about this topic, I'm by no means an expert. I was just volunteered, I think, to talk about this. So here I am. And this is not a lecture, so please feel free to interrupt me if you have any questions, comments, either unmuting yourself or posting in the chat. Can I see the chat? Anyways, so just feel free to interrupt me. I think it's better for everybody if you have any questions, we talk about it and then move on. Also, one expectation from you is that you are familiar with programming under Linux, and especially like compiling and programming, compiling, running, especially in HPC environment, like parallel programming, at least, even if you haven't written anything, just compiled community codes or other people's codes or help them compile and run. That will be the only expectation from you. Okay, let's get started. So there's basically two sections, two parts of this talk or this session. Debugging will be, I guess, like half of the session, and profiling and tuning will be the other half. So we'll talk about different debugging methods, not just C, C++, Fortran, but also like Python and R, because there's more and more users using those languages, not just standard C, Fortran, those languages. In the profiling and tuning, those topics aren't talked as much as you hear about debugging. So I try to introduce the basic ideas and some tools that are useful. So debugging is defined as, detecting and removing existing and potential bugs in a code that make your code crash or give you unexpected results. Okay? And also, it might, bugs might prevent you remove bugs to prevent the incorrect operation of the software. So basically, there are like syntax errors if you type the wrong syntax. For example, if you're switching between C and Fortran, probably do that, syntax errors, or if you are new, or if you're using different libraries, like the previous talks mentioned, so you make syntax errors. Those are easier to catch, easier to correct. Not always though. Seg faults, segmentation faults, like invalid memory access. If your loop, for example, try to access beyond the limits of your array, then you get into seg faults, IO errors, but no, these are just a few examples. The pie chart shown here shows like how much time takes for like designing, coding, and testing. This is not exact, but rough estimate. the basic idea is that, debugging testing takes as much as or more time than coding. So it depends on the project, but it usually takes the most time from my experience. So we use something called debugger to help you find these issues. I need to emphasize that no debugger can fix it. So you have to use a debugger to find those errors or bugs and fix yourself. So there are like command line debugging tools, graphical GUI debuggers, we'll talk about it. And latest, you can use ChatGPT as a debugging tool. I'm not going to go into details, but and we will not have any examples. So you have to try it yourself. It's rather new development within the last 6 months, 7 months, I would say. By ChatGPT, I didn't mean just the OpenAI's ChatGPT. It's all LLMs, large language model based ChatGPT, like, for example, Bloom's, or there's many. So you can use most of those to debug or help debug your code, especially Python, C, Fortran. Those languages are like much easier to debug with LLMs. So the next topic would be debugging using compiler flags. So we are not using debuggers yet, but we can use compilers themselves to help us find these bugs. So when you write a code, you need a compiler anyway. So why not use the compiler's capabilities to help you debug as well? So that's the idea. So these can, and the other point is, almost all debuggers require you to compile your code with -G flag or some variant of it or equivalent of it. Like, for example, if you use GNU or Intel compiler, you have to compile with -G. Compilers can help you debug during compile time, obviously, but they also can help you debug during runtime. Not always, but some issues. We'll talk about those in detail later. The downside is these are vendor dependent. For example, GNU compiler and Intel compiler has maybe same capabilities, but they have entirely different ways or flags to do the same thing or slightly different things. So that's inconvenient. And also version dependent. That's a serious issue. Like, for example, if you use an older GCC or GNU compiler, they might not have the newer options, like the options that newer versions have. So that's also not very helpful. So those are the issues that you need when you try to use compilers for debugging, but they are still helpful. So using compiler flags during compile time. Yeah. Again, this only serves as an introduction into this topic. There are like 50, 60 options listed in GCC manual or the web version of it. You can get into much more detail with that, but I'm just introducing these ideas so that you can go look for yourself. So one option is, warn all or W all. This works in GNU, Intel, C++, and Intel Fortran has -warn space all. So you can see vendor dependence and language dependent. Same thing with different flags. So that's what I said. Pi is inconvenient, but it's still useful. So this is actually a combination of many options That's why it's called all. For example, it detects uninitialized variables, find unused parameters. These are quite helpful when you try to compile a program the first time. So before you need a debugger, the compiler itself tells you, hey, you need to initialize these variables before you compile this or run this code. So that's quite helpful. It saves time because you don't go through the compilation step and then try to run it and then figuring this out using a debugger, versus the compiler tells you there's a problem, right? That saves you time and much more convenient. As well as implicit function declarations in C++, so those kind of things. So one extra is, it's an extra warning flag added. You can add to one all. For example, if you put one all and one extra, it detects unused but set variables. Now, one all only detects uninitialized variables. If you put the extra flag, it detects unused but set variable. So it's slight variation of the one all. Another flag I want to talk about is one W error. So you see, if you are compiling a large a program like maybe community code or something, and it'll compile for 20 minutes, 30 minutes, and there will be much more warnings and stuff. You will not even notice them until you look at the log. Sometimes it's convenient for the program to like crash or the compilation to crash when there's a warning. So this switch just that. So if you put this switch W error, it treats warnings as errors and make the compilation to stop until you fix that warning or do something about it. There's a GNU. These are also, I think there are Intel equivalent, but I didn't really go look them up and put it here. I think, and also W uninitialized that has an Intel variant. Check unint. It's once the compiling time if the variable is not initialized and being used. That's a very handy thing because your program might run, but it might give you unexpected behavior sometimes, right? Sometimes it's fine, sometimes it gives you the result that you can't really interpret because your variables is not initialized, so it can get any random value in that memory address. So sometimes it's 0, sometimes it's 100, sometimes it's negative 10,000. So depending on the value, you might get different results. So these are like really hard to debug issues, but easy to catch when you have compiler flags like this. Next, we talk about the runtime, the compiler flags that helps you during runtime. -G, we already talked about it, and check bounds in G4tran is something really neat. It checks, so for example, if you have an array, like I said before, if you have a for loop or do loop, right? If you have a loop that goes beyond your array dimensions, this check will catch it. You can do check all. It checks like much more than just array indices. You can read more about these flags yourself. Again, this is an introduction. More runtime flags. This is something I really like. ftrapv. It detects integer overflow and abort the program. So that's really handy, especially like I said earlier, if you didn't catch it during compile time, you might get unexpected behavior sometimes when you run your code. Sometimes your program runs fine, sometimes not. So that's really annoying and hard to catch. So integer overflow means, so just an analogy if you don't know what an overflow is. So older models of vehicles, I hope you've all seen this, but have like analog odometers, right? Theoretically, you can get to 999,999. And then when you go one more mile, it becomes 1 million, right? But there's no one to put at the front, so it becomes just 0. So that's an integer overflow. At least, I mean, the same idea works in digital world as well. For example, if you have 8-bit, I think 8-bit, if 8 bits is the highest number you can get, for example, and 256 is the number that you can represent, right? But if you want to add 1 to 256, this is in binary, and then you get 1 followed by 8 zeros, but there's no place to put that 1, so that's an overflow. So your answer would be 0 instead of 256 because you can't represent that number. That's an overflow. In actual programs, this will be like, if you have like signed integers, this will become negative 255, 254, right? So depending. So that's why I said sometimes you might get unexpected behavior from your program. It will not crash. It might crash, but it'll give you like weird results because you think you are dealing with positive numbers, but your positive number became a negative number and doing weird things now. So the F-trap, we will catch them in and abort the program runtime if there's an integer overflow. Also, FPE trap, there are multiple options. You can like have all the options like invalid, 0, overflow, underflow. This works on G4tran. These are G4tran options. These detects like invalid numbers, for example, square root of 1, -1, negative numbers, and division by 0, and overflow of a floating point operation. Underflow, like an overflow, a floating point can underflow. My example is from Python. So this particular Python version's like smallest number is 5 times 10 to the power negative 324. So I did 5 times 10 to the power negative 324 minus 1 times e to the power 324. And it gives me 5 times e to the power 324, where the correct answer is obviously 4 times e to the power negative 324, because that number is too small to represent. You might say, I don't really care, it's a really small number, so it doesn't matter. But if your loop runs through 100,000, 300,000, 10 to the power 300 loops, this will become a much bigger number and you will have much bigger issues. Or you multiply this with the Avogadro's constant, for example, and then to square it or whatever. So this might become a huge number, a huge issue without you knowing. So it's very handy to compiler to catch this. This is an example. So I have a Fortran program. The huge function gives you the largest number can be represented. So I'm just adding 1 to that number. You can clearly see that the largest number is 2,147,483,647. And when I add that to 1, it becomes a negative number. So that's an overflow. This program was not compiled with any of the options, so it just runs fine. But if I compile it with trap overflow, it'll just say program aborted and the code dump. We will talk about the code dump issue again, code dump thing again. We'll see how we can use that code dump. This is a Fortran, or this is a C example. Int max, for example, is the maximum integer. So you can see the same behavior. You add 1 to that maximum integer and you get a negative number. But if you do ftrap v, the program just aborts with a code dump. And you know that there is some problem, right? And also there, if you are running an MPI program, there is debugging support from MPI compilers. These come in as environment variables that you set. I wouldn't get into detail, but these are really, really handy. For example, if you use OpenMPI, there's MPI param check. If you set it to true, it'll check MPI function values for illegal values. And in pitch2, there's MV2 debug show backtrace, which will give you like a detailed description of what functions executed in what order for this to crash. So those are really helpful. And also for those to work, you don't need a -G flag. Like you don't have to compile the program with the -G flag. Debugger basic. So this should be debugger terminology. I changed it to last anyway. So just few words, like few terms that we need to know before we get into debuggers. A debugger is a program that helps you find bugs in a code. And a breakpoint is something that pauses execution of your program and your code execution. There are different kinds. There are unconditional, the default, it always pauses at a certain point. This could be a line number or function, or it's up to you to pick whichever, where you define the breakpoint. And there are conditional breakpoints. It only pauses if a condition is satisfied. An evaluation breakpoint is where you pause the execution and run a separate code fragment outside of your program. And there are watch points. A watch point is you stop the execution of the program every time a variable changes value. Right? That's very helpful when you want to see what happens inside your program. We'll see some examples later. A backtrace is, list of function calls currently active in a process. Let's say in your program, when you run a program, it's list of function calls that are currently active. A frame or stack frame is everything in the memory. For example, local variables in the currently active function. There may be multiple frames when you run a program. Again, we'll see some examples later on. These are just terms that we're going to use. Serial debugging with GDB. GDB is GNU Project Debugger. It supports C, C++, Fortran, assembly, and many other languages, but not Python or MATLAB, those kind of high-level languages. It's extremely robust, built in mid-80s, and it's still being actively developed. It can start a program, make your program stop on breakpoints, we just discussed earlier, and you can examine the program after it's stopped and change variables and do many things to figure out the behavior. It's a terminal-based or text-only CLI debugger. The GUI front end is called DDD, Data Display Debugger. I didn't pay any attention to DDD just because the previous release of DDD was 2009, and it wasn't really working with most new systems unless you tinker with it. So, but last month they had a new version after 15 years, 14 years. So it's too late to make it to this talk, but maybe next year. So this is just a screenshot from their website. I didn't do this analysis or anything, but it's a really neat utility if you like GUI debuggers, and it complements GDB. Yeah, you are welcome to do your own research and find out about DDD. I'm sure they have much more new functionality. I haven't spent any time looking for them. Oh, okay. I have to show this slide like this. I know this is a problem. Okay. Okay, I lost some of the animations. Okay, so I have a simple Fortran program that calculates the area under a curve, a sine curve, I believe. Yeah, it's a sine curve, and it's just a simple trapezoidal rule. You don't need to know about this code. It's just a simple example. So I compiled it with G-Fortran. The program name is trap.f90 with -g flag, and I call it trap. And then I run it with GDB trap. And I defined two breakpoints. Break 13 means I have a breakpoint at line 13, and break 15 means I have a breakpoint at line 15. And then I run. Run means I run my software, right? The trap program. And then it runs at line 13, which is the breakpoint, and it shows the line. Then I can print the variables. Notice that it stops at line 13, it doesn't run the line 13. So print A means whatever happens to A before this line. If I print the area, I get a negative number. That means I did not initialize it, right? So it has some random value. This line did not run. So then I type next, and GDB runs one step, one line of the code, and it stops at line 14. It shows line 14, and then I want to see the value of the area calculated in line 13. It's a really small number, right? Now my area has a non-random actual value. I type continue, and it continues until it reaches the next breakpoint, which is the line 15, because I said break 15. It prints the line, and then it lets me do my thing. Like I can look at the variables or just continue. This program does not have a bug. I just wanted to show how GDB works. So with or without bugs, you can analyze your code or other people's code with GDB. Only thing is it has to be compiled with the -g flag. Any questions so far? I cannot see the chat, so I'm assuming somebody will tell me if there are any questions. Okay. Okay. Serial debugger GDB. So this is another example. This program definitely have a bug. I'm allocating an array with 5 elements, but my loop runs for 100,000 array index, but I did not compile it with the proper warnings or flags to detect it. So I'm running it as if it's fine. So now the GDB runs the program, right? And it says, okay, the program received has a seg fault, right? And then now I have to see the issues. So to do that, so I do the backtrace. Backtrace tells me what frames. I mean, we talked about the frames in the terminology slide. So this is a simple program. It does not have multiple functions or anything, so it has only one frame. So it has number 0. This #0 means it's frame 0, so it has only one frame. But if you have a large code base, then there may be like 5, 10 multiple frames. So you have to go into different frames to see where exactly the problem. So I go into frame 0, and it says, okay, frame 0 is this xi equals I, and then I can print the variable value. I can see it's 30,000, which cannot be. I mean, x cannot hold that many values. I can print x, so it has only 1 to 5, so I can clearly see what the problem is. I'm choosing small examples so that we can have a look at these options, but in reality, this analysis is much more time-consuming and lengthy. Useful GDB commands, you can have break command. We talked about the break. You can do location, thread, or if condition. You can specify the break with line number or function name, etc. And you can clear the breakpoints, remove. If you just do clear, it will clear all breakpoints, but you can specify clear breakpoint, say 13, that will clear the line 13 breakpoint, or you can say breakpoint, like if you specify by function, then you have to say clear breakpoint trap, for example. And step is where you can go one step into your code. Say you stop at certain breakpoint, and then you can say step. If you just say step, it will move one line. It will execute one line. And if you say step 10, it will go by 10 lines. Next is much similar to step, but it does not stop inside the function. For example, if you call a function at a breakpoint, right? Step will execute that function. Next will not stop at that function. Step will. So usually, depending on whether you want to go into the function and debug it, if it's a system call or system function, you probably do not have to. But if it's your own function and you don't know whether that's the issue, then depending on that, you use either step or next. You can skip source or function files. Reverse step is something really neat. You can run the program backward. Like you can do one or more steps back. Right? You can stop at line 13 or line 15 and then go reverse step to line 13 to 12 or 13 to 11 or like that, and undo, so to speak, the behaviors. For example, you can change a variable value and then go to, backward and see what happens. List will print the lines of source code. So set Y is also really important. You can not only print variable values, you can set variable values. Info locals will just spit out all the local variables in the current frame, right? In the memory, right? So that's, especially if you are doing this in a batch mode, this is really helpful. We will have an example later. Henry, can I get a time check?
Yeah, your time slot is through 4:30. I think that's 5:30 your time. So
Okay.
you've got about 39 minutes left.
Okay. So we talked about code dump analysis earlier. We saw how a code dump was produced when we used the compiler flags. And a code dump analysis is really important to figure out what exactly happened in these crashes. You can use GDB to open a code dump file and go inside and read it and see what happened. You can use, exact same commands that we just looked at, backtrace, frame, list, and like print, but you can't change values and those sort of things, obviously, because it's not dynamically running right now. It's a record of the previous crash. So you can't change anything, but you can only look. Also, you can create a manual code dump of any perfectly fine running process with G code. I just wanted to put it out here. This is an example of code dump. This is the same thing in the overflow. Yeah. So I got the code dump from the previous overflow example, and I ran that code dump through GDB. So the syntax is GDB, the binary name, and the code dump. It tells me things that I don't need to really need to pay attention, but then I get into the prompt, GDB prompt. Then I do BT is backtrace, the simplified form. Then I get 0 to 6 frames. These things I don't need to pay attention because I don't control these. These are system side. And the 6th frame is where is main, overflow.c, line 5. So that's the only thing that I control, that my program. So I go to frame 6. So it tells me this is where the problem is. Of course, that's where the I is the largest integer, and that's how I got the sec fault. Again, this is a really small example, so there's not much to do in here to find the error, but in a realistic case, there will be a larger analysis. Parallel debugging, like I said, in high HPC setting, we use more than single node to solve a problem. You can use GDB, and there are other user-friendly GUI debuggers such as Total View and DDT. The only difference is, one major difference is they are really helpful, user-friendly, and GUI-based, but they are expensive. GDB is mainly terminal-based and free. Okay, so parallel debugging with GDB You can, this is not just for parallel process, but even for serial process, you can attach GDB to a running job. If you have a running process and you want to see what's going on in that particular process, you log into that node and to GDB program name and process ID. The way you, if you are unfamiliar, the way you find process ID is using, you can use like top, or I mean, top is the best tool if you are not very familiar with, this kind of thing. If not, you can use PS, AUX or something like that, but that's more complicated. Also, you can run your program under GDB like we did so before. After you attach your GDB to your process, you can do interactive debugging, but only within that node. If you have 256 processes, you can't really possibly log into all 256 or multiple nodes and debug each and every process. So you have to know what you are looking for. GDB server is a better option, but it's much more complicated setting up and talking about it. So I've left it as an advanced topic. So I will just say you don't have to log into each process. You can say from your head node, you can connect to all the processes and debug processes with GDB server. I am giving a simple example of how to do interactive parallel debugging with GDB. If you use Slurm, for this to work, if you use Slurm, your administrator has to allow the --x11 flag, or if you are using PBS, then they have, I think -x is by default, so they don't have to allow anything. So I allocate 2 cores in this case, right, with X11, and then I have, for convenience, I define xterm GDB args as a variable, and then I do either MPI run or srun MPI GDB and your program name, right? So this will interactively run your program through GDB under Slurm, for example. Under PBS is, I don't have the commands on top of my head, but the process is similar. But I mean, under Slurm you can do srun, but under PBS you just do MPI run. When you do that, you get 2 terminals or 2 xterms, and you have the GDB prompt in both. Right? And by the way, you are not now not logging into 2 nodes. You are in your head node, for example, and then you have 2 xterms. But again, if you have 256 processes, you can't really do this. You can't have 256 terminals and look at each of them and see what's going on. But this is only manageable within, let's say, 4 or 5 nodes or processes. So the problem is now I don't know which node is the rank 0, right? So I need to set up a breakpoint to find out what is the rank, right? So for that, I can either set up a breakpoint at the line number. This is part of my code, line number 48, or I can set up a breakpoint with the function MPI comRank. So both will give me the same result. So when I do that, so I try to print the rank on the node 74, it says 0, but on node 76, it says 110. That can't be right, because I only have 2 processes. So the the problem here is, we stopped at line 48. That's my breakpoint. But this line was not executed yet. So this is garbage data. It doesn't have any meaning. I had to go to next line to execute this. Okay? So I go to next line, right? And then if I print the rank, now I get on node 74, I get rank is 0, and 76 is the rank 1. So this is the head node, this is the worker node. After I figure that out, the analysis is up to you, depending on what you are doing. Right? For example, I set up a watch point. Usually you do not set up multiple breakpoint on worker nodes, but just as an example, I did it here anyways. But again, depending on what you want to do and how your program works, you might want to do it. Right? So this is an example of setting a watch point for any variable. So I'm printing those values and continue. Excuse me. I will not go into much detail in the interest of time. So that's how you could go on interactively debug using GDB. The limitation would be you can't debug the real production code that runs on hundreds of nodes or using hundreds of cores. But you can, if you can, in some cases, you can minimize your number of cores to say 4 or 8, then you can see the picture of what's happening and then debug using GDB. Non-interactive parallel debugging. It's much easier. You don't need any special setup. You run GDB in batch mode. So you tell GDB, I'm running in batch mode, and then put your commands in a text file. And then provide your binary name and run with MPI run or it's run. So your commands is, for example, this, break at the function trap, and then run the code, print the rank, info locals that prints all the variables, and then continue, for example. This is the trap function I wanted to look at. And when I run it, I will get a file. My Slurm output will look like this. I omitted some sections so that I can capture the entire thing in the slide. So I ran this on 4 cores. So I have 4 breakpoint notice. And it prints the rank. In this case, it's 2 and 3. For each rank, it prints the local variables. This goes on and on until the loop is complete. This is just a simple example for non-interactive debugging. This is really helpful when you have more than few processes. But then the problem is you end up with huge text file with a lot of verbiage, and you have to go through each line to figure things out. Total view and DDT. These are, like I said, you can debug serial and parallel programs. These are GUI debuggers, a lot of features, really easy to use. Most people use it the GUI way, but they also provide CLI option as well if you need. Total view has a extra barrier called process barrier. It's a point to synchronize all the processes. When you have in GDB also we put by hand we put breakpoints, right? So in total view, you can do this with process barrier. Like I said, there are a lot of options, and also you can do remote debugging. For example, you run the total view, you run your job, and then you connect with total view GUI on your laptop or your head node, and then you debug remotely on the cluster. It helps debug CUDA, and it does reverse debugging, which is really handy. It's called replay engine. Just like GDB's reverse stepping, Total View allows you to replay the process, those steps that your code went through. So these are the options that it has. You can stop the hold the operation and go to next step. You can hold the pause the operation. You can go to next. You can do step. These are same as GDB. You can go out of the step, and you can kill the process and stuff like that. You can do all these operations for the overall code or each node or each process, like in the, and you can set breakpoints in the GUI. This is the stack trace. These are all the variables in the stack at this moment. So what's happening in each rank? So per each rank, you can click on each rank and see what are the variable values. So this is you can open multidimensional arrays and see the values in a GUI rather than just in the terminal. And you can put breakpoints and run through your code and really analyze your code and understand what's happening. DDT is much similar. It's a different vendor. That's the main difference. They also allow Python debugging, and all the other options are much more similar. So the only difference would be, the price you pay. So CUDA debugging with GDB. This is something I wanted to mention. So this is something NVIDIA provides. You can debug your in C or Fortran code with CUDA GDB. You can go to read the documentation. They have really good documentation about it. It's free, and you can do CPU and GPU debugging with it. It can do GPU code dump as well. And it does remote debugging, just like GDB. Intel Inspector, this is not a complete debugging tool, but it's provided free from Intel. It's mainly useful to locate memory issues, deadlocks, data erasers, and also it's a GUI. It has a CLI version, the terminal version as well. You can run it. The way you do is you do the CLI, you run the CLI version with your MPI application, you run with your job, and then you use the GUI version to visualize the results. It really comes handy to analyze, problems, usually memory problems, but it's not a complete debugging tool. But I just wanted to mention it. Language-specific debuggers, like I said, Python and R are really popular these days. And if I didn't mention about those tools, it's incomplete. So Python has PDB, Python debugger, which is really close, similar to GDB. Even the commands are much similar. So it's built-in tool. You don't have to install anything. You can run Python-m PDB. and your source code, you can do interactive debugging, batch debugging with it. I'll show some examples in the next slide. And most R users are using RStudio, so I'll just talk about RStudio. So RStudio provides debugging tools. You can set breakpoints in the RStudio or put browser function in the code. I'll show you an example in a minute. So this is Python debugging. Like I said, you run with Python's PDB module, you run your code with PDB module, and then you can do like print variables. You can step in, go to the next step and print variables. You do breakpoints, and you can list the code and do a bunch of things. So these are some of the useful commands you can. You can see these are mostly similar to GDB, except the where command. It just prints the current position and stack trace. The reason I wanted to mention is, a lot of people use Python and all, but PDB isn't very popular. So, because when you script or program in Python, it's most people are left with print to debug their issues, but Python has a built-in debugger that not many people are using. So I wanted to point that it is there and it's really handy, and it's similar to GDB. R debugging. So I'm not a big R user, so these are not like, I just found this from somewhere and put it in the slide so that our users can at least know about it. So you can click on the RStudio and put breakpoints, and you can do interactive debugging with the next, continue, stop. They have all the commands on the RStudio GUI, and also you can have conditional breakpoints using browser command. You can put browser in your command in your program, and you can do interactive debugging, or you can do batch debugging like this. So if you put browser in the places that you want to debug and run this code interactively, you can look at the values, and also you can do the same thing with non-interactive batch mode. So it also provides like similar functionality to GDB and PDB. I have only very limited time to get into profiling and tuning, but that's a very important section. So I'll try to at least give a good introduction. So profiling and tuning is something that not many people are familiar with, especially in HPC setting. The P stands for high performance, right? So in HPC setting, performance is something we really care about. So to get higher performance, we need to understand what are the bottlenecks of our codes and get rid of those bottlenecks to have increased efficiency. So to do that, we have to profile our codes, and then depending on the results, we have to tune it. So profiling is finding the bottlenecks, and tuning is basically resolving those bottlenecks. There are many profilers like gprof, Tau, and Intel tools. So these tools are really helpful. Again, these are similar to debuggers. They don't profile, like they don't tune the code for you. They'll only pinpoint where the problems are. So it's your job to fix them. gprof is, again, like GDB. It's from the GNU project. It's the GNU profiler. It's a text-based CLI tool. it provides a flat profile, something called flat profile. It's a breakdown of time spent on each function call. For example, this. So this program has functions called energy, update, submit, and this is listing. So 44% of the time is spent on energy function, 34% of the time spent on update, and about 20% in submit. This is cumulative, so it doesn't add to 100, by the way. It's in seconds. So you can see where the bottlenecks are. So it also tells you how many number of calls, right? So per call in this code, submit function has the like as a function, submit function spends most time, takes most time, because energy function takes 44% of the time, but it's ran like 86 million times, something like that. So, but submit function ran only 800,000 times. So this is an actual example. So we ended up making the submit function parallel to remove that bottleneck. So to do that, this was the first step. You profile the code and see where the bottlenecks are and see what you can do about it. And a call graph is, how your program executed. Like, in this is the same program. And so main function, it calls move and it calls locate and so on. This is only part of the code graph. So gprof can profile serial codes. So you compile them with PG option rather than -G for debugging. So use PG for gprofiler, also gprof, and you run it, and then it generates the files, and then you read those files with gprof. In this case, thermal. I run gprof thermal. Thermal is my file name. So it provides the flat profile and the call graph. And you can do the same with parallel applications with a simple tweak of the way you run. Tau is really neat performance analysis, tuning. It's called tuning analysis utility. It's a really nice performance toolkit. It has a ton of options. You can profile Fortran, C, C++, Java, Python, many languages. The only issue is it's really complicated and steep learning curve, but you don't have to learn everything. You can learn, the part that you really need to profile your code, and then, use it to find the problems with your code. So it does something called instrumentation. That means it puts source code fragments in your program. When you recompile your code with Tau, it puts these code fragments in your code so that it can measure. It can be memory, it can be how many time is spent on each call, and can be like many different matrices. It measures these events. It calls events, right? It collects samples and generate profile information. Okay? And you can read these files, but that's not very helpful. And it also provides analysis tools to read these files and generate visualizations so that you can look at it like this. So this is an actual program profiling. So you can see MPI send function spent like an hour. This is like more than 24-hour running of a program. So it spent like a day, like an hour on MPI send, and then it shows you where this functions calls coming from, the line numbers, like source. This is a suite of program. So it says like step 2 read.f90. So these are like multiple source files. So it shows you source file and what line numbers this function came from, so that you can easily go find them and see what you can do about it. It does also something for tracing. That's like, it's similar to call graph. Like it shows you how your program is executed. So all these colored sections in the real example, you can actually click them and see what they are. These are functions, and these lines are data movement from like between the nodes. So tracing is a record of how things ran in your job, in your program. So like I said, I only spoke about fraction of the capabilities of Tau. It has a lot of other capabilities. So depending on what you want to look at, you can do that. You can probably do that in Tau. Call graph in Tau, it's not a text file. It produces a nice visualization of a call graph. This is really helpful if you have a really complicated program that has hundreds of different functions. So in real diagram, you can click on each of these and see what they are and where it's coming from. Also, it provides you the communication matrix if you want to debug MPI or the communication aspect of your program. Intel Advisor. So like so the Tau is really nice, but it's complicated. If you want something simpler, Intel Advisor might be able to help you in some aspects, at least. I have an example here. It's only a vectorization. It only looks at some aspects, not every aspect like Tau does. So it's not a complete replacement for Tau. I will skip this in the interest of time. And Intel vTune, these are all free tools. I wanted to introduce, this helps with MPI profiling. Again, if you combine all these Intel tools, you can get some functionality of the Tau, but not the complete replacement. And Intel Trace Analyzer. So that's for tracing. So Tau does profiling and tracing. So Intel Trace Analyzer specifically do serial and parallel tracing codes. Okay, so profiling Python, like I said, people use a lot of Python, but they don't use Python debugger, but I haven't had any, like most of users using Python profiler. It's really neat, it's built in. There's C profile and profile, but C profile is the most like low overhead version, so we'll use that. It's really easy to use. You run it with, you run your code with C profile, or you can import it in your code, but this is the way most people prefer to use it, so that you don't have to change your code. And you can see your timing of your functions and all the information. This is whole program profiling, but you can also do targeted profiling. But for that, you had to load it in your code and enable and disable depending on what you want to do. There's line profiler. It works similarly, but you only profile lines. One thing I want to show is the memory profiler, which is really important because Python consumes a lot more memory. So if you want to know where all this memory is going, so you need to use memory profiler. Some tool like memory profiler. This is not a built-in tool, so you have to pip install it, but it's still very helpful. You can look at these examples. The slides are posted, so I'm just going through them, introducing. R has RStudio has a built-in profiling capability, so you can profile R codes. Last section is tuning. I appreciate a few minutes. So tuning, like I said, is a manual process. You use the information from profiling and tune it. So this is, so to speak, an art rather than, any specific process. So you need experience with tuning, but there are tools that you can use so that you don't have to spend years tuning your code. You can use better algorithms, and that's the first step. And then compiler flags can help tune your code. You can try with different compilers. You can use optimized libraries and things like that. Compiler flags. So always compile for yours or specific machine type that you are running on. That's really important to get. I think previous talk they mentioned about this tool. Compile for your own architecture rather than compile for any. That this gives you much more performance. So I will skip this because we already seen about this. Compiler flags. There's like GNU, Intel, all these compilers provide optimization flags. There's O2 is the, there's O1, O0, O1, O2, O3, and OFAST. So depending on the level, you get different optimizations turned on. So I did this exercise with Pansat algorithm and a naive two-body simulation. I ran it with O0, O1, O2, O3, and you can see from O0 to O1 there's a like nearly 2 times performance speed up, performance gain. So with O2 and O3 you get slight gain, but depending on the program, you get a better speed up. But you have to be careful if you use something like OFAST, you might not get numerical accuracy. So you had to watch out. Mako is a tool that really can help you, give you clues about tuning. This is rather new. I think it's developed in like 2015 or something like that. And I have been using this only for a couple of months. So, but I can see it's really helpful. And you don't have, it's a performance, it's a profiling tool as well as a performance tuning advisor, but I wouldn't talk about the profiling part because we talked about that already with other tools. So Mako gives you reports. It can generate reports and give you suggestions on how to tune your code. For example, it analyzes your running code with optimizations and everything said. And it tells you about, okay, so you didn't, in this code, I didn't specify O2, O3, or fast. So it tells me you're missing the optimization flags. And I haven't specified I didn't build for specific architecture. And it's telling me you have to, choose your architecture to get more. And also, a fundamental loops is missing. So I have to compile with these options. This can be really helpful if you are new to, tuning codes and, compiling. So it has ton of information and like in plain English, so to speak. So you can better understand it. And it, for example, this is part of the report it generated. It tells you why and what to do with to improve these different aspects. Right? So vectorization, how to, and it gives you workarounds. This might not be like very useful for a seasoned, programmer, but if you are new to this kind of exercises, this can really help you. And also you don't have to compile this software. It comes as a binary. So you just have to download it and run. So also try different compilers. In some cases, Intel compiler gives you 2 times performance. Great. For example, WoW. But I run LAMPs, I get no performance gain when I switch to Intel. So your mileage may vary. So your package, your software might run faster with different compilers or might not. And also try with OpenMPI, MPH2, Intel MPI. These may or may not give you performance boost. Use performance optimized libraries. So we switch gear a little bit, and so the next option you can do to tune your code is to use performance optimized libraries. So in what we do is we solve numerical problems, right? In HPC or in most cases. So these problems can be divided into small pieces of tasks that are say atomic tasks, I would say. For example, solving a differential equation, or solving a set of linear equations, or solving a matrix, or inverting a matrix. Sure, you can use Gaussian method to solve set of equations, but never do that. There are better algorithms available to do that and gives you much more performance. So look for different solvers and experiment with them a little bit and see what gives you the most performance. This might take you some time, but it'll save you a lot of time when you are really using your code to in your production runs. For example, like BLAST and LAPACK are the 2 basic libraries. Basic linear algebra subprograms, BLAST stand for. It does vector, matrix, matrix routines, basic linear algebra, basically. So you can look up for the functions. I'm not going to go into detail, but there are a lot of implementations based on BLAST, Open BLAST, Bliss, and Atlas, MKL from Intel, that's also free, and CUDA BLAST, the different implementations or variations of BLAST. LAPACK is built on top of BLAST. It's also a linear algebra package designed to solve linear equations, eigenvalue problems, LU factorization, for example. And the parallel version is KLAPACK. These are really popular basic linear algebra packages. So these are few, this is not a complete set, but few basic numerical libraries that are being used, like BLAST, LAPACK, Hyper, FFT West, Eigen, ScaleLAPACK. These does not depend on any other library, but these are building blocks to many other libraries, such as these. For example, sweet sparse and trilinos, these are matrix solvers, sparse matrix solvers. And also MUMPS is also sparse linear equations solver for HPC, or for example. And sundials is a differential equations and difference equation solver. And CGAL is a geometry algorithms, like computational geometry algorithms. Armadillo is it's like a linear algebra library. It's matrix mathematics mostly. So these are like, and also Scotch and RPAC. There's like ton of these libraries. You might see these are like doing similar things, but depending on your exact task, one library might be better for you than the other. And there's HDF and HCDF. These are like IO related libraries, input output. So it's kind of numerical libraries, but super helpful in input output related tasks. So I just want to emphasize that, don't write your own solvers and look for the solvers that are being used by other people. That's the most important thing. Community support and is these are all open source. So if there's no community support, and if it's something that somebody invented 10 years ago and nobody picked it up, then you probably should not use it. But if it's something that's being used for few decades, then you should go for it. There's a reason that other people are sticking with it. But performance might be different depending on your specific task. So you have to experiment with this a little bit to, get the best performance. And that's all I have to talk about, Henry. And thank you for listening to me.
Do folks have questions or comments, either by voice or in the chat? Okay, so thank you so much for this talk, Prasad. Wish we had more time to get into more details. If you ever made a YouTube channel, I'd subscribe. It always felt daunting to me getting started.
I skipped most of the slides, but I think I gave you like a complete intro at least.
Yeah. Are these libraries only for C?
No. Even if the library is in C, there are Fortran, like there's Fortran bindings. But I think the question is more about like, can we access from Python and such, right? I don't think they're asking about, okay. Some libraries are, right? It depends on the library. So you have to go see the library. Most of the libraries I showed here are for, C, C++, Fortran, but, Python has a huge community support, so you can pip install anything. For example, like there's a lot of like data science based software support to libraries. So these libraries are mostly for C++ Fortran community, but there are a ton of libraries that's the same thing, and based on these libraries are specifically for Python and R as well. If there's a question about whether they have MPI support, if there is no MPI support, then there is an equivalent library that has added MPI support for it. So go find that. Most libraries, if it's being widely used and there is, chances are there is MPI support for the library that you are looking for. Any other questions?
All right, that looks like it's it. Let's give Prasad a big round of applause, of virtual applause. Thank you very much, Prasad. That was really fantastic, and we can see people got a lot of value out of it. And I'm going to stop the recording.